Okay, let's begin. Um, as usual, thank you very much for coming. And please interrupt me whenever you want, also online. And so you remember last time that we finally completed the definition of a topos, right? And if you don't remember all the axioms, that's fine because I don't need it today. The question is that what is the next goal? And the next step is just to construct many toposes. And more specifically, I need to introduce three ways, three different families of categories that are toposes, right? The first that we will see, I guess, today and next session is what a geometer calls the category of sheaves. And sheaves, whatever it is, I will explain, is kind of backbone of the modern geometry. And the same guy is called forcing when you talk with a logician. So that's the thing. The second is what's called the Heiting valued sets. And we may be familiar with the specific case of Boolean valued models of set theory, which is kind of equivalent to forcing. And the third is something that the proof theorist would call realizability, which is kind of a technique to extract information from proofs, computational information, I mean. So the first two are somehow the expansion methods. So you have your usual sets, and you add some sort of, in the first case, you add some sort of variation that, okay, I can vary my sets over time somehow, and then I get more than just the usual static sets. The second is that I'm expanding my values from 0, 1 to more, right? Again, expansion. The third is kind of restriction. So in the first two, I'm working with sets and functions between sets, and then I expand it. In the third, I restrict it to say, there are different things, but say from all functions between two sets to all computable functions between sets, right? And again, I have a topos. So since it's a topos, you have kind of foundation of mathematics. You can develop many things, roughly everything there. It is set theoretic-like, but at the same time, everything is just computable. This is just the best possible word, say, for a computer scientist, right? So you do your mathematics in a synthetic way, but there is computational content there. Okay, let's see these three. First, the first. We had the axioms of a topos, and I won't just repeat them, but we saw that we have three examples, right? We had, or more than three. So we had set, of course, and set to 2 or set arrow. This is just my baby variable sets. We had the category of all G actions, right? And also we had the category of all quivers, let's say just graphs, but directed with multiplicity. All of them are plus this stupid category. All of them are toposes, right? Simply because these are just our running examples, right? We always checked everything kind of roughly in them, all the three axioms, and these are all toposes. So my first task is just to generalize this to one construction, right? They are all different versions of one construction. So what is it? Okay. For that, I need to introduce the two main things that I'm kind of delaying because I want to just lower the cognitive load. Functors and natural transformations. Finally, we have to see them. Okay, let's do it. What is a functor? So we talked about that a category is some sort of algebraic structure with objects, two sorts, morphisms, some construction, functions between them, etc. So what's a functor then? It is just the map of the structure. It is the structure preserving map. So if you have two categories, you have actually two classes, right? So you have objects, you have morphisms, right? So a functor is kind of a pair of two functions, right? Let's say f0, f1, right? A functor from C to D. Objects to objects, morphism to morphisms, respecting everything. And what is everything? Source and target as two functions. Therefore, I mean that if I have a map from A to B, then f1 of f, whatever it is, must be from f0 of A to f0 of B, right? And usually people just don't like to write f0 of 1, so we call it just f for both of them, and sometimes it is confusing because sometimes morphisms are objects in another category, etc. But that's what it is. So therefore, it means that we have this, right? And then the other two structures are identity. So identity must go to identity, but if identity is from A to A, then f of it should be from f of A to f of A, so it should be identity of f of A. And then you have to respect the composition. Of course, here in C, here in D, right? What else? So, and so there are some obvious examples. Say, I said that the category is just a combination, a common generalization of a poset, the order, and the composition. So then if you have just a poset as a category and another poset as a category, say here in Q and P, then what is a functor? If you read them as a category. Of course, I have to go from objects to objects, so a function, and then maps to maps, but you have just at most one map. It goes to the only map there. Simply, I'm saying that if A is less than B, f of A is less than f of B, and what about these two guys? Because I have just one morphism, always I have the equality between anything. So just order preserving. The other, so if I have one object and one monoid over it, and another object, one monoid over that. Let's say this for n, this for m, if somebody cares. So what's a functor then? Object goes to object, just one object, right? So you cannot do anything else. Morphisms to morphisms, such that it's just a homomorphism. So
what are the is it the group operation? I'm not quite sure what you mean by one.
No, this is a category. No, and not the category of G sets. It is just one object, and morphisms are just the elements of a given monoid. So the whole point is that you can read a monoid as a category with one object, but the elements in the monoid are just morphisms, right?
Structure of the monoid appears in the structure of the morphism composition.
Exactly. So more identity and composition, yes. So Therefore, functor is just a common generalization of the order preserving and the other. So some set theoretical ones. What? Like this is a functor from set to set. I have to read an object. So P. I have to read an object and maps it to another object. So let's say that just the power set of A. Huh? Why not? And what is P of F? So if F goes as a function from A to B, then P of F should be from P of A to P of B. What is the natural choice here? Exactly, image of the subset, right? So it is a function from power set of A to power set of B. So I have to define it. Oh, sorry, thanks. This is B. So P of F of some subset of A must be just F of that subset, the image, right? What else? Of course, I have to check it is a functor because identity does nothing, right? Etc. There is another one, P kind of opposite. It's contravariant from opposite to this. So the same on objects over set of A, but backward. So if you have a map from A to B, then I have to come up with a function backward, meaning that it should go from P of B to P of A. And how to do it? Inverse image, right? So what else? So these are so of some S. S is subset of B, then it is F minus 1 of B, right? Again, it's a function. You have to check. Yeah, millions of these guys, right? So from set times set, you can go to set. You read an object here, it's a pair by definition, and you map it to product, and you read to a map here. A map here is just a map from A to C and G from B to D, right? Two maps, then there is just one canonical map here, right? You go there, etc. Plus blah blah, right? So you can do, sure.
Just to be sure, so here contravariant just means normal, but from the opposite category.
Yes, exactly, exactly. So therefore, I just define functor, but you know, because it depends, right? It depends which one is just your real category. So because set is our real category, then it is contravariant, but otherwise it is variant, so covariant. So anyway, you can come up with many examples, right? Point is that I want to change this obvious picture, right? So for us, a functor is just structure preserving map. That is just exactly extremely dumb, right? So you have to come up with better intuition. So that's just not a very good intuition. And I want to deliver 3 of them together with some examples, right? And I'm sorry, but today I have to just deviate a bit into sometimes algebraic geometry, topology, whatever, right? Just to convey the idea that these guys are more than some algebraic notions. Okay, first, the first interpretation is that you can read a functor as a construction method, right? So let me write functor as a construction method. What does it mean? It means that it goes from C to D you can think of C and D as two discourses, right? And F reads something here, change it to something there. So the obvious example that we all know, and it is kind of the reason that we have category theory in the first place is just from algebraic topology, right? So you have the category of topological spaces, the category of groups, say, and some maps between them. Let's say that I have functor, right? So what does it mean? It means that I have a construction, I read a topological space, and I transform it to a group. Why? Simply because it is easier to work with groups than topological spaces, right? It is some sort of invariant, right? You forget some of the data and pick the part that is easier to handle. So you don't need just that huge example to see these forgetful functors. So for instance, you can goes from groups, say, to set, forgetting the structure, right? So you read a group and just provide the group itself, but as a set, and read the morphism and say the function of it, right? Simply, I'm using this U to work with the same data, but in the greater setting. Therefore, I'm forgetting some of the structures, right? And also, maybe I have to say that we have also some free functors in the other way around, so something like this. So then you read some set and you construct a free group constructed with the elements of that set. And of course, then if you have a function from some set to another set, then you can induce, of course, some obvious homomorphism from this to that, right? So there are also free or forgetful functors. But coming back to this example, so that is a very important thing, right? So people usually say that we use these construction to show that two topological spaces are not the same, right? Because if you have isomorphism here, then F preserves isomorphism and you have isomorphism there. So for instance, they say that there is something that's called pi1, right? The homotopy group. And then pi1, say, and I have these two spaces, right? So this is my B, just the circle, full field circle, I mean. And then I have S1, right? And then the point is that you can compute pi1 easily in quotation. So this is just a trivial group. This guy is the group Z. I don't care what is pi1, but the point is that there is a functor with this property. And of course, then you can show that these two are not the same because the groups are not the same. The point is that checking that two groups are different is easier. And also computing the functor is easy, kinda. Therefore, I can prove this. Okay, but why functor? So this is the part that's missing usually in the usual story, right? Because as long as I do something with some space, and as long as I don't use, I construct everything up to isomorphism, right? This is just what we usually do, right? So then I can do this, right? I don't need just to define this guy over morphisms. Right? Because my construction here has two parts. I know how to transform a topological space to a group and a continuous map to a homomorphism. And I'm saying that the second part is not just needed, right? At least for this argument, as long as, you do everything up to isomorphism. That's wrong. So you can do many things with the functoriality, and this is why they usually insist that everything should be functorial. So here is my dumb exercise. So exercise. Let's prove that. So there is a map, the inclusion map, right? This is a part of this, of course. My exercise is that there is no R here such that this guy is identity. That's kind of weird, right? But there is no R. How do I know that? No continuous R such that the composition with the inclusion becomes identity. I use the functoriality of pi1. I transform the problem to a problem in groups. Then it would be, okay, let's say that we have R. Then if I apply pi1, it would be from Z to 0 to Z identity. That's impossible, of course, right? Because the first map just kills everything because it's Z in between. And what's the point of this? Because then using this, you can show that, I don't know, the usual proof that any map from this guy to itself has a fixed point, the Brauer's fixed point theorem. Simply using the non-existence of R. It's just one line proof, right? Point is that, and you can prove it for Bn, for any n-dimensional, if you have the good group here, right? The point is that it is really important to work not just with isomorphism, with also other maps. Okay, so this is a construction method, and I have to say that this is not the case that all the construction methods are functors.
So when you were just saying that Simon, I talked about functors rather than functors, yeah?
Exactly. But of course, when you think like that, we are working with categories, of course, we have to deal with maps. But when you think of topological spaces, it's not necessary to think of it as a category. So it is also some sort of emphasize that you have to consider whatever you have as a category. So, okay, that's not the case that always everything is a functor, I have to say. There are some construction methods that are not functor, yeah? So should I say one? Why not? So changing the subject, so we know that usually when you have a topological space, that is very good to investigate the ring of all the functions to all continuous functions, of course, right? And this C is a function, of course, from topological spaces to, say, rings, right? But technically opposite because it changes the direction because X is here, right? Okay, that's a very good way. So you can use algebra to investigate topology. But then sometimes we get crazy to go backward. To say that is it possible that I read a ring and pretend that it is a ring of functions over space, and then I have geometric intuition, right? To work just with some algebraic thing. So if you think about this example, and I would explain, so the idea is that if you have a ring, if you start with a ring with the C of X, then X must be just the set of all maximal ideals. Okay. Because any point is just the functions that are not zero at that point, and it is a maximal ideal. Okay. So you can identify points with maximal ideals. And that is kind of the usual intuition in algebraic geometry. But the problem is that this construction, mapping R to all maximal ideals, is not functorial. What? Exactly. So let's say that, of course, if it should be, then it should go from what? It should be in opposite direction, right? It should go from this to top. Huh? On the rings or rings homomorphisms in topological continuous maps, say. Yes. But of course, you need some sort of topology. But my problem is that even this does not work. So let's just forget about topology and go to set. the base set. You have to have some base set, and it is not even functional. So why? Because if you go from R to S, then you expect to have some sort of map between the ideals, say maximal ideals of in the reverse direction, right? And the natural map is just the inverse image. The problem is that the inverse image of a maximal ideal is not maximal ideal. That simple fact forced algebraic geometry to consider all prime ideals because it is functorial. The inverse image of a prime is a prime, right? So it is really important to be functorial. Okay, so that completes my first part of the story as a functor as a construction method, and it is kind of easy, right, to see. The second is less obvious. So functor as a variable object. So let's say that I have a functor from C to D. I can, okay, so if you have a function from X to Y, you can say that it's a function, or you can write it as f of X with parameter X and say that it is a variable element in Y, right? It's an element in Y with a parameter in X. That's a good intuition sometimes, right? So you can do the same thing here. You can write f of A, right, as object in D with parameter A or variable over C, and C is your time structure. That's also a good intuition, right? So actually we had one of these examples, right? So if C is this poset and D is set, what's the functor? Any functor. Exactly. Object to object, so two sets, one function between them, right? This is the data. Two sets that are usually right like this, right? Two sets, one function between them. And I call it a variable set for a reason, because it is just a variable set. Functor from this very obvious structure. You can change, of course, to something more interesting. Say, I can change my, maybe it's good to have three. So I can, of course, change it to a poset, right? Let's say that I have a poset. A functor from a poset to set is what? It's a variable set over the poset. If my poset is forcing poset, then this element is the one that you work with in forcing as your new set, right? Or even better, maybe I can just use any category as my time structure, because then I have more morphisms. And we will see that it is actually crucial in forcing. You cannot do all the forcings with just this, right? Okay, so then what? As a variable. So this is just more temporal intuition that I have here. But it is also possible to think of it as parameterized. So the best example that I have comes from algebraic geometry. So let's work with this story. So let's say that I have some, okay, we all know that algebraic geometry is about the roots of polynomials. So this is my polynomial. Huh? And we want to investigate the roots of this guy. Okay, the question is where? The usual classical attitude is that, okay, go for the biggest possible, with all the roots in quotation, And then you have all the information, because if I investigate this guy in Q, then I have nothing, right? It's empty. So I go for C. That's good. That's a very good idea. So as long as you work with just one variable. If you have two variables, then something is missing. So let's say that I change it to this set of equations. What's the root? Yeah, empty. You cannot have something like that, right? There's no zero. But there is a zero. So what's a zero here? This guy is this. This guy is this. Sorry. They meant to be parallel. What's a zero? Exactly. There is a zero, but you cannot see it. So then they say that, oh, so we have to add the points at the infinity. You go from the usual thing to project, right? And then there are also more obstacles, right? You can say that, okay, what about this? What is the zero? It's just 1 0, but it is just two. You have two zeros, right? So then how to count this? Again and again and again. So you have to add more points at infinity, complex, I don't know, with multiplicity, etc., 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 to be rich enough to see really the behavior of the set of roots, right? The modern approach is different. It says that, yes, we are interested in the zeros, but as a parameterized object. Zeros of this were in a ring, and the ring is the parameter. So let's say that I have this, for instance. Who cares? Something of that sort. This is just my set of equations. So I'm interested in the zeros of this. Where? In R. So you read your ring, and then V of R is just the zeros of, say, this set I, right? And of course, it's a subset of R squared, because you have two. And of course, it depends on R. So then maybe you have a function. In R, you sign just the zeros. What happens to F if F goes from R to S? There is a canonical map. There is a canonical function from VR to VR, right? What is it? Of course, if I have a root in R, F of it is a root here, simply because F respects everything, right? Addition, multiplication, the elements in Z, right? So I have a functor. The modern approach is that zeros of this, you want to investigate this, you have to investigate V as a function, as a parameterized object. Because then you can see, you can say that I have the whole information of the set of equations, right? Without missing the point here or there or whatever. Okay. So, what are the categories exactly? So it is a functor from, people write commutative rings to set. You read a ring, you provide the zeros as a set, say. Subset of R to something, but I don't care, set. It's a set at least, right? So, fine. Not 100% sure, but okay.
Well, I mean, a good example where the zero was infinite.
Yes,
That's not
of course. Yes, but then the point is that okay. There is more into the story that I can't tell really, right? So you cannot see the points at infinity really this way. But yes. Yeah. What's the universe? Yes. So this V? Okay, so you have some size concerns that where it is as a set theoretical notion or what? Right. Okay, what's a functor from commutative rings to set, right? It's no, it of course it depends on the set of your equations. So what I'm saying is that if you have a set of equations, exactly, exactly. But then my claim is that this V really encodes the whole behavior of the equation. And that is a correct point, but I have to just sweep it on the rug. But we will see something slightly close to it later. So, okay. So the point is that you can see that infinity thing also, but not via these kind of functors. So to any set, I'm assigning some functor. There are also other functors that you have to investigate. So there you can see them. So functors are good enough, but not just these guys. These are affine. But anyway, so what I'm doing? Yes. Oh, the second. Oh, yes. This guy as a variable. And the third is just easy. The third is as realizations. So three functor as a realization. What do I mean by that? So let's say that I have a functor from C to D, right? So D is just a real category, a category of sets, groups, whatever. C, you read it as just a graph, points, arrows. So points and arrows are just some abstract figure, right? You realize it inside D. Example. So if I have C as this category, two objects, one morphism, it's just an abstract thing. So what is a functor of from this C to set? Two sets, one morphism. So I'm realizing this thing as real objects, real sets, and real functions. So if I have C as this guy, so one object, some group over that, as we had before, it is some sort of abstract object and abstract symmetry, right? If I have a function from this C, the set, then what happens? It maps this guy to a set, these guys to real bijections over that set. So I'm realizing this abstract thing as real sets, real functions over that, right? And that's a cute one. So what if C is just empty? The empty category. No object, no more. What is this? Like a function from empty domain, there is just one functor here. Some trivial functor. Right? So there's just one trivial functor. And then that's also good. So what if I have two nodes, two maps, abstract? Realize that would be what? Two sets, two functions, really. What is it? A quiver, a graph. Edges, source and target, vertices. right? So on and so forth. So, but I can say now that, by the way, I just unified all the examples that we had before, right? So that is a variable set. This guy is a G action. We see this later. This is just a graph, right? So therefore, the objects here, the objects in all these categories, okay, one is just that one, right? So 0. So the objects here are just functors from some fixed category to set, right? So this is the way to unify that. I have to use this notation, say set to C for some small category. Small means that everything is just a set. And objects of this are just functors from C to set, right? And you can interpret them as realizations of C, variable sets, I don't know, constructions, parameters in C, whatever, right? But everything is set theoretical with some sort of parameter. Okay. What happens to the morphisms then? I have to unify them. Functor for the objects, natural transformation for the morphisms. But before that, I need to say something else. So I need to, what should I do? I need to work with some other functors. From my story, something is missing, right? The best functor ever is what? Is the home functor, right? So let's say that C is a category, then there is a functor C opposite times C to set. It reads a pair here, maps it to all the maps from A to B, the home. And what is home of F? Okay, that's bad. All the maps point. So what is this? Because if it's a functor, I have to define it also on the morphisms. So what is it? F must go from, say, C to A. Okay, no. Let me be honest. So from object AB, I go to the object CD with FG, right? And here I have to go from this set, all the morphisms from A to B, to all the morphisms from what? From C to B, right? And since it's a set, I need a function, right? So this should be a function. So what's a function? So the first point is that F is a map from A to C in C opposite, meaning that it is just a map from C to A. So now I have two maps actually, right? I have a map from A, C to A, and from B to D. So how to do it? You have two maps, this way, that way, and you want to go from all the maps from A to B to all the maps from C to D. You just compose. You read fine, compose it with these two, and then you get whatever you want. You have to check that it is a functor, and for that you can see that you need that the identity is really the identity and the associativity of the composition. That's cute. So that's a very important functor. Of course. So the home functor. Home of A and B is the set of, yes, all morphisms from A to B in C, right? And let's say that I have a map FG from AB to CD, and then I have to define home of FG as a function from set.
Any reason why?
Okay, so this is a category, right? The objects are pairs of objects of the first and the second. So therefore, I have to define it over an object here, which is really a pair by definition, right? So don't read this as just binary thing, right? So it is a category. I have to define something like this, right? From some D to set, right?
Not to reverse the direction of apples.
Yes. So
Really.
What?
It's just, I'm just,
it matters really, but I will explain. So you want something like this, right? A function from this to this. So let me define that function. So I'm saying that home FG of phi here is just a composition. So in the right order, who knows how.
it's really helping. The thing is, you've got the on there.
Yeah.
C on.
Yes.
So you should be considering a pair of functions f and g, where f comes from C on.
Yes. True, but it is hidden somehow here, right? So it's a map in C opposite times C. And so it would be useful if I open it up, right? So by definition, a map from a pair to a pair is just a pair of two maps from the first to the first, second to the second. So F is a map from A to C in C opposite. G is from B to D in C. So if F is from A to C in C opposite, it means that it is really a map from C to A in C.
Okay.
So now everything is in C, right? I have a map in C.
Yeah, I'm asking you to write this.
Got it. So, okay. Let's do this part. Okay. So if it is the map here, so it means that F is a map from A to C in C opposite, right? And G is a map from B to D in C, right? So this first guy simply means that F is a map from C to A in C, based on the definition of opposite, right? And I also have my G from B to D. This is my data. And what should I do? I have to define home of this guy as a function from this home to that home, right? So then I say that the home of FG as a function reads phi and do the obvious composition that I didn't know how to.
Fine.
Yes, phi, it should be here. So I go from A to B, then from B to that. But first I have to go from C.
What subobject is fine?
So what is this? The home of this guy is a function. Okay, this guy should be a function, right? From home of AB to home of CD, right? I have to define a function.
I thought defining
A function, right?
this functor.
Yes.
So you go across the set.
Yes.
So
To any morphism, I have to assign a function, a morphism here. So that's a function that I want. And to define it, I say just treat phi and do this. Okay?
here the phi is an object in the set.
It's an element in this set, right? In this set.
But in the category of sets on the right.
Yes, yes.
On AB is a
Set,
object.
object, which is a set. And if it's a set, so if you want to define a function between two sets, you have to say what you have to do to the elements, right? So, okay, that's weird functor that we have. And it encodes really the whole information of the category. So, and it is possible to just fix one of these two things. So if you have home goes like this, come on, always. To set, then I can fix one element here or one element there, and I get a functor, right? So like this. So let's say that I fix this A, then I get a functor like this that you can write home A dash that goes from C to set, and it simply reads B, right, as an object here, and computes home of A of B. A is fixed, always. And then you read a map from, I don't know, something to something, and then you do exactly this whole thing, but this F, the first guy is identity, so you do not do anything there, right? It is just composition from this side, this side. You can have exactly the same idea here, but then it goes from C opposite to set, right? Same idea. Fix it and always use identity for it, right? So you can say that this functor kind of encodes the behavior of A, after A, kind of, and this is before A, right? The maps coming to A and going out. So these two encode the behavior of A, kind of. So the last thing that I have to
Sorry, you said
sure.
the functor encodes category,
Yes.
and this is how it does it.
No, that one really encodes the category in the sense that what is a category? You have some objects, and then the main thing is just the morphisms between them and composition, right?
You mean the image of the functor?
No, the whole the functor as not really, because sometimes you are forgetting some structure, sometimes you are adding some structure, right? So the point is that to think informally, the whole information of C is what? Is the morphisms between objects. Okay, just morphisms, let's say. Do you accept that? It depends. So sometimes if you have no, it is just a very informal intuition, right? So nothing formal. Okay, so I love these two functors. Everyone does, and the point is that they are very good for many reasons. They are called representable or co-representable functors depending on your C, but I don't care, so I call all of them representable, right? Simply because you can represent the functor via one object. So let's say that you have a category C, you have a functor, two sets, that's important. I would call it representable if F is essentially one of these two, right? And this essentially, there is a formal meaning of it, but we will see it later. So, for instance, what? For instance, that P functor that we had, right? So this P, it was from set opposite to set. This guy is really representable, right? Representable by what? Can you find your A? it should be this setting, right? So I have to find some A such that, so we don't know what it means, but essentially this is kind of the same as home of X to something. To what? To 0, 1, exactly, to 2. Subsets are just the characteristic function, right? In any category. I didn't come. Okay. What else? That U functor that we had from set to, what's it now? From group, sorry, to set. This guy is represented. Right? So if I read G, it should be U of G, home of something to G. Right? We are in this setting. What to G? This is home in groups. Right? So homomorphism from something to the group G should be kind of equivalent to the elements of G. Integers. So if you want to go from integers to G, you have to just choose one, right? And then say one goes to where? And then everything is canonically determined, right?
Just for the previous example, where you said
Yeah.
you're starting with some category.
Yes.
In this case, the problem is
No, this. The opposite. Okay, my C is set. Yes.
the original category is that these zeros are set in one direction or another.
It is just the reverse direction, but yes.
You're considering this following map on the category set.
Yes.
In this case, you're considering on category groups.
Yes.
And you say the example.
Yes. So you simply just read the group and just spits out the group itself, read the morphism and do the same, right? So it does nothing. But the point is that, yes. So, okay. So now what I'm saying is that this U is representable, meaning that I have some A in C, meaning that some group in,
Let's see the groups.
yes. So G is from the group. This guy should be a group. This home is inside the group, like this home. This is the home in C. So the homomorphism in groups. This set of all homomorphism must be kind of the same thing as the elements of G, because this is just G itself as a set. If you have a homomorphism like this, then the corresponding element, as Howell is saying, is phi of 1. And this correspondence is a bijection, right? Because of course, if I have any element here, I can define it as phi of 1. And then expand it, like phi of n is just obviously n times phi of 1. And I can do it in a unique way. So there is one-to-one correspondence, right? There's no more information in homomorphism from Z to G other than picking phi of 1. And then the rest is just automatic, right?
And it won't work for something else instead of Z.
No. So let's say, I don't know what, Z2. Then if I, then F, then phi of 1 should be something with the order 2. So yes.
But again, the object for the thing on the right is the object.
Yeah.
The homomorphism to the
Exactly.
But
Exactly.
U is throwing away
The group structure and read G as just set.
Oh, so then choosing homomorphism is the same as choosing.
Exactly. Exactly. Yes. So you can do more examples of this kind, right? So what? That's that thing that we have here. So if you can move me, Neil. So this VI is representable. So let's say I is just the equation x2 plus 1 equals to 0, y equals to x3. And this is my V from rings to set. And this guy is representable. Meaning that I have to come up with what? I have to come up with something like, so this is my I, my V index I say goes from rings to set, and I have to show that it is representable, meaning that if Vi of some ring R must be equivalent to home in rings of some ring to R. What is that ring? The same idea as here. So V is just the zeros, right? It's a subset of R squared. The zeros of these two are equivalent to morphisms from what to R? Okay, first let's say that we have R2 here, right? Let's say that I have R squared, right? So everything is a zero, so, right? So then it is represented by what? Picking two elements is equivalent to a morphism from what to R? No? Exactly. So Z, X, Y. Because if I know where I have to map X and Y to, then that's it, right? So everything is automatic. So, but this is not R2, it is just this set. So it should not be any X and Y in R. It should be the zeros of these two. Therefore, exactly, the quotient. You do the quotient, right? Over the ideal of X squared 1 and Y minus X3. Okay? You make them 0. So a map is just choose X and Y such that in R as two elements such that these two become 0. So that's represented. So I forgot to mention a functor, the pullback functor, but who cares? I can. So maybe that's good to see. So there is a subfunctor, right, from C opposite to set. So it reads objects, and this is just all sub-objects, right? Huh? What's the morphism? If I have a map from B to A, which means from A to B, right? Then backward, I have to be able to map a sub-object of B to a sub-object of A, right? Because sub of F, whatever it is a function from sub B to sub A, right? I read a subject of B, And what is the corresponding subobject of A? Subobject of B? Pullback. Pullback of a subobject is a subobject, right? I'm assuming that I have pullback, right? So, and then you have to check that it's a functor. It is a functor. And even better, sometimes this guy is representable. Let me do this here. So if it is representable, then sub-objects of A must be somehow in correspondence with maps because it is opposite from A to this is similar to the power set. Exactly, to omega. Right?
I thought you were saying subjects be just money.
Yeah.
Is that right?
Yes.
But for this to be true, I guess you really have to work with equivalence classes of money.
Yeah, it depends.
Otherwise,
That's true. That's true. Because yes, because right. It's not unique, it's unique up to isomorphism, so I have to make it really unique. That's true. Right? This is another way of defining a subobject classifier. It is just a representing object of this sub A. Okay. It's not the case that everything is just representable because it seems so, but it is not the case. So if you pick something at random, most probably the guy is not representable. And these are just very good functors. And this is the reason that they are representable, right? So let's say that if I go from set to set, like I read A and add one element to it, like in disjoint union, right? This is not representable or co-representable or whatever. That's just bad, right? But sometimes there are some things that are not representable, but kind of they should be. And that's a philosophical important thing. So, for instance, this sub, if you compute it from topological spaces to set, like not all subsets, all subspaces, the guy is not. The guy is not representable. I'm saying that in topological spaces, I don't have the subobject classifier. But that's bad, right? I have to have the best subset, subobject, subspace ever, right? Because we had the best subset ever. That's impossible. Again, like the exponential, that's missing also here, so you can solve it somehow by going to bigger categories, but I don't care. The good example that I love is this. People say that algebraic geometry is about investigating the zeros of polynomials. Okay, fair enough. So if I go here, so we saw that if I have just some polynomials, you have to investigate this functor. And this functor is always representable because just you do the quotient over the equations, right? And when something is representable, it means that the whole functor is encoded somehow to one object, right? If you investigate that object, A, you investigate the functor. That's the good thing about it, right? So everything, then every zero, blah, blah, is encoding here, right? Which means that the whole algebraic geometry is just investigating some rings. So it's commutative algebra. There is no algebraic geometry. It's just a subset of commutative algebra. And that is just plain false. And the reason is that we don't just investigate the zeros of polynomials in algebraic geometry. We investigate more, far more. And one example of the functors from C rings to sets, which is not in this form, is the following. So let's say that V goes from C ring to set, and V of the ring R is all the pairs in R squared such that there exists CD in R such that AC plus BD equals to 1. So all the pairs that, the ideal is just a whole. And V, if you have a map from R to S, then it really maps A to B to FA and FB, and then it preserves this property, whatever. So, okay, this is weird, right? So, why I have to be interested in something like this? Because based on some formal intuition that I won't explain really, the idea is this. So if you have just R squared, so let's say that my VR, like dropping the mic. So if VR is R squared, right? Let's say that I have this function. So what is the geometric version of this? Just a plane. I'm investigating the plane, right? Kind of. Like a whole plane. This guy corresponds to the plane minus the origin. That makes sense, kind of. You may say that, no, maybe the better thing is just this, define this minus origin. Huh? You don't want origin, just kill the origin. What's bad about this guy is that it is not functorial. Origin. Minus origin. Yes. So that's the natural definition. It's not functorial. It's not functorial simply because it is possible that you start with something not in the origin, but f of it is the origin. Right? That's bad. So how to make it functorial? This is the canonical. I won't explain that, but let's say that this is just the classical complement. That is the intuitionistic complement, and that's the right one. Right? The same idea as we had for the implication, right? So what was the implication between opens in some O of X? So you say this, but that's bad. Therefore, interior of it. Right? This is the same idea. Okay, so this is, of course, some geometric notion to investigate. And it is not representable. One can't prove it. And it should be, because whatever objects that we are investigating, if they are rings, that's fine. But maybe we need more also to investigate this. And this is the reason that why people go from affine scheme to schemes in algebraic geometry. But there is some logical point as well. So if you have just equations in algebraic geometry, you can quotient. If you have quantifiers, you can't. But also we are interested in existential quantifiers in algebraic geometry, really. So this is important. Right?
You're talking about algebraic geometry as studying roots of polynomials.
For
example,
yes, that's.
And then you started here, and you wrote down this definition.
Okay.
Just meant to be that V is what?
V of R.
The V is a function.
V as a function. Defined like this on objects. On morphisms, you have some canonical function here. So you have a functor. What I'm saying is that in some sense, this functor corresponds to the geometric object of the plane minus the origin.
Maybe I don't want geometry. You're abstracting what you're doing on the.
No. There is some sort of correspondence that I'm not explaining, right? So just believe me that this geometric object is there, is that functor. And this is the reason that this functor is interesting. Okay. And we have to investigate it in any sort of algebraic geometry. My point is that this functor is not representable.
You mean representable on this homomorphism on commutative, this home thing on commutative ring?
Yes.
That's
So this guy is not home of anything to R. Therefore, there is more into algebraic geometry than just rings.
If you're interested in.
These guys. In what?
I thought you were going to say there's more to algebraic geometry than representable.
Exactly, but representable functors are representable by something, and that something is the ring. So therefore, you can say that representables are common, kind of the whole theory of rings, right?
So you're saying you always want to keep representable functors, but you're going to go beyond rings to get what you want.
No, what I'm saying is that there are some interesting things. For some reasons, we believe that they should be representable, but they are not.
In ring, oh, we should.
Exactly. So then you have to expand your category of rings to make these guys representable. Intuitively speaking, it means that you are expanding your discourse to new objects.
You're saying you're going to get down a new definition in a minute because you want to study the plane without.
Kinda, yes. Okay. So I said everything that I wanted to say about functors. But it does not mean that we are at the end. So let me say something about something even worse. Natural transformations. Again, there is some sort of dumb explanation that you have functors between categories. So what are the maps between functors? Natural transformations. So it explains nothing. Let me motivate it like this. So let's say that f and g, we interpret them as variable objects, right? Or objects with parameters. So you have two objects with parameters. What is a natural map between these two objects? So it is f of a with parameter a, g of a with parameter a. What's a natural notion of map between the two? These two guys are in D. So one map in D. Because these are objects in the variable. So the maps should be also in the variable, right? That's just the natural thing. So let's say that we have some alpha. For any A, we need one, of course. So then the natural candidate that I have is some sort of sequence, say, of alpha A's from f of A to g of A for any A of the objects, right? At any point for any parameter, you have a transformation. Okay, that's fair. Yeah. But of course, it should not be arbitrary. Right? You have to somehow respect the variation in C or the variation in parameter. So what is the variation in parameter? So let's say that I go from A to B, and this is my variation. That guy is in C, of course, right? And here I have f of A to g of A. When I'm in A, then this is my transformation. When I'm in B, this is my transformation. So, of course, when you go from A to B, you have to transfer this map to this map. It should not be arbitrary, right? There should be some continuity. So, via what? Via, of course, f of f and g of f, right? So therefore, I need this to be commutative, always, formally. If I have two functors between two fixed categories, f, g between c and d, by a natural transformation from f to G, I mean a sequence like this of maps from f of a to g of a indexed by objects, such that, not any of them, such that for any map in C from A to B, this guy is commutative. Right? So one good, because this is kind of changing F to G in smooth way, right? So one intuition is that these two guys are some sort of spaces because they are graphs. These two guys are continuous maps because they preserve the connections. And this is the homotopy. This is a way to transform F to G in a smooth way. Right? So you can also read this natural transformations via the functor as a construction, right? So let's say that I have two construction methods. How to transform one to the other? Of course, you transform it pointwise. Let's say that I have two construction. I read a topological space and I compute a group in two different ways. How to transform one to the other? Of course, for any topological space, for any input, I have to be able to do that, to do the transformation. But it should not be arbitrary simply because arbitrariness means that this guy is not uniform. Yes, I'm changing f of a to g of a for any a, but I want it to be uniform in a somehow. What do I mean by that? So let's say that we all know that what? A times B and B times A for any two sets, they are isomorphic, right? There's a map. Of course, this map, which is the swap map, depends on A and B, on the domain. But kind of it doesn't, right? Because it's just swapping, right? I don't care. How to capture that? I would say that, okay, if I do it for A and B, the swap AB, and if I do with C and D, these are different things. But if I go here and there with two maps between A and B, then I have the commutativity. So it is some sort of uniformity, right? That this is really transforming F to G, not any F of A to G of A. The construction F goes to the construction G, right?
But this is an example of an apple transformation.
Yes. And that's a very good question. Because it would be confusing, I start with easier ones. But I come back. So some examples of natural transformation would be the following. So no, I have two, C and D, two functors between them, and the natural transformation goes from one to the other, from one functor to the other. Two categories, yes. These are just fixed, but then I have two morphisms, right? Okay, so example. Whatever you think it's natural is natural. So say, first, the best way to think of this is just to write it like FAGA, some map between them, but then we can check that it is natural, right? Then I also write the functor things. But the idea is simple, right? So if I have set A, this is set A, and the power set, what is the most, it's also bad, but whatever. So let's say I have A and I have power set of A. There is some obvious map here, right? You read one element, you compute the singleton, right? mapping A to just a singlet. This guy is natural in A. They call it like this in the parameters. It's natural in A formally. So I have what? I have a functor. I have set. These are my C and D's. This guy is what as a functor? What is the functor? Yeah? How is it? No, the first one. Identity, exactly. Identity, of course you cannot see that. What should I do? Maybe this is good. Identity functor, right? Do nothing. And what is this? P. Yeah? And natural transformation means a sequence for any A of functions. So my sequence is really this. So these maps, right? So let's say a singleton map from A to PA for any set A. This is my natural transformation. But I have to check something to be a natural transformation. Let's check this. So if I check this, then you do it for A, you do it for B, and you check that it is natural. It's uniform. So if I go from A to B with some function f, then f goes here because of the identity, P of f, which is just computing the image, by definition comes here, and this is commutative, simply because if you start here, you have singleton A. If you compute the image, you have f of A, which is just A, f of A, the singleton. The image of a singleton is a singleton range. That's not true. What else? You can go from, actually, okay, that's hard. Easier. This one. Right? For any AB as sets, the projection is natural, really. Formally, it is the categories are set, pairs of sets. This is what? This is the product functor, right? And this is what? You read a pair, but you just take care of the first. It's a projection functor, right? Maps AB to A and maps FG to F, right? It's kind of forgetting the second guy.
So it's this cross on the left. Cross at the top is the actual one of coding, realizing this in sets.
Not really. So this cross is just pairing, nothing else. So I'm really saying that I don't have just one set, two sets. That's it. And this says that this one. So then if you have two sets, you can do two things with them. Either you do the product of the usual Cartesian product, and the second is just forget. These are the two things. And then what I'm saying is that you have this natural transformation. So why it's natural? Because if you have A times B to A, you have C times D to C, and for any F from so from A to B with F, from C to D with G, right? Which is a map here. So you have F times G. Here you have just F. And these two are projections, say for AB, projection for C. Of course it commutes, right? So you start here, you have your A here, right? and then f of a, or you do pointwise f of a, g of b, and yet you forget, right? So formally this, but usually they say that this guy is natural in A and B, right? In the inputs. So you can have many examples. So I'm a bit over time, but let me just at least complete this game of basic examples of natural transformations. So I said that sometimes some functors are essentially the other, right? So I mean really natural transformation. So like this. So let's say P of A, this P of A, and the home of A to 2, of course, they are not the same things, right? Functions, subsets. But they are essentially the same things, meaning that there is some natural isomorphism here. So just one way of it, so this one. So how to do that? You read S as a subset, and you make the characteristic of S, right? That's natural. So formally, it is what? It is from set opposite to set. This is P. This guy is home. This is the natural transformation, right? So why it's natural? Because this. So if you have that, if you go from, say, a function from A to B, right? So then, because it's contravariant, so you have this. So this is just f minus of something by definition. And you have this home of A2, you have a home of B2, and this guy is just composition by definition with F, and that guy is the characteristic, right? So you have to check that it commutes. And it really does. I'm going to say that's too much, right? Or the other one that we had.
And if the inverse is natural,
What?
the other direction.
Yes. Yes. Yeah. Both of them are natural. And what? Then we had this. We had that. U from groups to set, right? And then you had home of Z to set. And we had this function, right? That Pavel mentioned. So you read some function and then you compute phi of 1, right? This is natural. So everything always is natural. So this map from, say, any set A to power set of A. Okay? But this power set. So what is the map? You map A to all the subsets of A such that they have A. This is just the backbone of stone duality, right? This is natural in A. And so for naturality, the obvious example that everyone likes is kind of the vector space version of this. So you have a vector space and you map it. You go from that to V star star, which is just the home of V to R. This is V star. So do this guy twice. So like this, it is home to 2, you do it twice. Home to R, twice. So always you have this map, right? So you have, if you have some sort of category, you have a map like this, right? So let's say I fix one object, what it is, from I, and then I define A star as home AI, but you have to have some structures and then I iterate that, right? So there is a natural map, and then the map from V to V, sorry, V star star is this. So it reads an element in V, and then what? You need a function, and the function is say f index V and f and index V, read something in V star, and then do the application, right? That's just a natural function. So it's the equivalent of all the sets, such sets. Okay. So this guy is the backbone of Sloan duality. That's kind of trivial. And then you also have other versions like, other dualities. There are many, like Priestley duality, whatever duality. The Gelfand duality. So the Gelfand duality is something like this. You go from X to C of X. Right? C of X, you remember it, right? So home of X and R. So we go from X to the function that reads another function and apply it on X. So that's just the general idea. Okay, so that's some examples of natural transformations. Next time, I start with an example that is really natural, but it is not natural. But before that, the only thing that I have to say, we will check it next time, but the only thing that I have to say is that if you have, okay, we saw that, let's say that the objects are morphisms, functors, say, from this to set, right? So then we expect the natural transformations as maps between functors are really the transformations here, the morphisms here, and we remember that guy, right? In the definition of the variable sets, it was there. So we will check that actually that set to C that I promised is the category with objects are functors from C to set, and then morphisms are natural transformations, right? And what difference is this guy unifies all of them. We will see that this guy is really a topos. This is the mother of all the others. But still we are this far from the complete real forcing. Yeah. That's just the baby forcing. But with it, you can prove the independence of continuum hypothesis, for instance. Can we? Of course we can. No, we can. Yeah, we can do anything. Simply because if C, no, that's right. So if C is a group, okay, my concern is that C makes it intuitionistic, so that's bad. But if C is a group, then it's just a permutation model that we have forcing really. Okay, sorry. Any questions? Or you want to kill me? Sure.
The very last construction, that might any proposal will be like proposed to the category.
Not really. So the thing is that the natural condition is that C enriched over set, meaning that the homes of C are in set. If you have similar thing like that, then yes, you can do it. Sure. Bye-bye. Sure.